Hey guys, my name is Adrienne and welcome to Organic Chemistry 1, Part 11 of these recorded sessions. Today we'll be going over, for most of y'all, Chapter 11 and in general, alkynes. So for everyone, this is the last chapter, the last section for you guys in OChem 1. And that's great. You made it this far. And here is the agenda for today. So alkynes, preparation of alkynes, addition reactions, and then miscellaneous reactions. So, you know, pretty straightforward, pretty same format as we've been doing before, structure, properties, degrees of unsaturation, naming, things like that, and the reaction. So with that being said, let's get started. So alkynes, we know triple bonds, right? Alkynes, triple bonds, again, hybridization sp, linear shape, right? And 180 degrees. And again, no rotations, nothing like that. And it has this formula if it's just a straight chain, CnH2n minus 2, right? Which makes sense because those two pi bonds are taking away the hydrogens, obviously, right? And the trends apply, boiling point, melting point, solubility, things like that. Um, it can be terminal, internal, you know, which is, you know, obviously, right? And then again, bond dissociation, pi bonds are easier to break than sigma bonds. So alkynes are definitely easier to get reactions with than single bonds. And this is going to be the most electron rich out of all the um, chains we talked about. So very electron rich, making it a nucleophile, right? So again, just the basics, but don't forget any of these. So again, high polarizability, high polarity, right? High polarity. And now we move on to, let's go to a new page. Actually, no, it's in here, degrees of unsaturation. Again, it's going to be 2C plus 2 plus N minus A halogen minus hydrogen divided by 2, right? So alkynes have 2 pi bonds, so right off the bat, they have 2 degrees of unsaturation, right? And that's all, right? And then from there, you add other pi bonds or you have a ring or something like that. So automatically have 2 pi bonds, 2 degrees of saturation. So now let's go to naming. Nomenclature. So IUPAC rules stay the same. IUPAC rules, right? Longest chain, things like that. Now what's interesting here is that now what happens if we have a double bond and a triple bond? We know that parent must go through triple bond, right? Must go through triple bond. But what if we have two? So if we have two, this is important. Um, the chain is numbered, giving the first site of um, unsaturation, so either a double bond or a triple bond, the lower number, right? So not necessarily triple bond isn't more prioritized than double bond. It just depends if both of them are there, we number whichever we hit first. Do we hit the double bond first or the triple bond first? So that's what we're gauging it on. So that's really important. And just one common name for triple bonds, and this is the smallest or I guess shortest double bond. It's just that, right? It's called acetylene. Acetylene, obviously. And then um, a more IUPAC friendly ethine. So acetylene, aka ethine. So you'll see that a little bit later with the reactions, but you know, this is just one of those things that's common that they're not always gonna draw out for you. That you kind of just have to know that acetylene is just two carbons triple bonded together, right? So with that being said, let's do some practice. So in this video, the videos are getting shorter and shorter, right? But that's good because we're learning faster and faster. We're getting used to it more. So not too bad. So name these molecules. So okay, okay, that looks kind of crazy. Okay, and then this one. This one's also pretty crazy because okay, and then last one. Six. Okay, so actually, let's do this one. Let's change this up a bit. Um, okay, so pause the video and tell me what you guys get. So for the first one, you guys should have gotten four, four. I don't know why. Okay, dipropyl, one heptine. Right? So we number from here, obviously, one, two, three, four, five, six, seven, and these are propyl groups, right? So not too crazy, nothing too difficult, right? What about this one? You guys should have gone for this one. Three isopropyl, one five octadiene. This one's a fun one because um, so we have obviously we're numbering from here one, two, three, four, five, six, seven, eight, and this is our thing. There are three isopropyl, right? And then one, five, we have two triple bonds, right? But we have the di after the octa, right? Octa is our parent, and then there's two dienes, two triple bonds. So that makes sense, right? And what about this one? You guys should have gone this two etheno one cyclohexanol, right? So we numbered from here. One, two, three, four, five, six, right? And then all is our parent because alcohols are more prioritized than any alkane, alkene, or alkyne, right? And ethanol is what we were just talking about, right? So nothing's crazy. And actually, trans, trans two ethanol, one cyclohexanol. So nothing too crazy, just same old naming. But it's fun, right? It's easy. Um, it's one of those things that you're for sure going to get on a question, right? Easy points. So now let's move on to preparation. of alkynes. So same as with alkenes, right? We can prefer alkynes, and pretty much the same thing, but we double everything, right? Same thing with the elimination when we were preparing alkynes, pretty much the same thing. And in this case, we need our vicinal and geminal, right? Two leaving groups, basically. Br, so it doesn't matter, but this one, 2Na plus, NH2 minus, first with excess. This one, KOCCH3, 3, DMSO, and then just to mix it up, two equivalent, which is the same thing as excess, right? So, here, oh, this should have been 1, 2, 3. Okay. This should have been straight, but you guys get the idea, right? So, yeah, and that's all there is to it. We eliminate both of these, and we make a triple bond. So, and if we didn't have excess or two equivalent, then we would just make a double bond, right? Because we would just have one of those things, so we can only eliminate one leaving group. So make sure to pay attention with excess and two equivalent, right? Okay, so let's do some practice. And this is pretty much the same as the examples I gave you already, but you know, let's see. Let's draw them out. So find the products, right? Okay, so take a second, pause the video, and show me what you guys got. So for the first one, you guys should have gone something like this, right? Nothing too crazy. Um, and they, looking at it from this way, where were these made? These were made over here, right? Because obviously you can't add over here because then this carbon over here will have like 6 bonds, right? So we can't do that. So they went over here instead. And for this one, you guys should have gone literally just that, right? This is where they were made, right? So again, nothing too crazy, nothing too dramatic. Pretty simple. From, if you guys are familiar with the alkenes, same concept, but this time we're just doubling everything up, right? We have two of the leaving groups, we have two of the reagents, and then we have two of the pi bonds, right? Okay, so now addition reactions, right? Addition reactions. So you guys are probably, you know, well aware that as long as you have pi bonds, you can have addition reactions because you just take away the pi bond, add 2 bonds, and you're good, right? And that goes back to our concept a couple videos back. Addition reactions are take away a pi bond and then add 2 sigma bonds, right? Whether that be a halogen and a hydrogen, or an OH group and a halogen, or whatever, right? You're just making 2 pi bonds out of a 1 pi bond. So, and again, as I said in that video, addition, substitution, elimination, they're all the same concepts, and you apply them to all these reactions, and it doesn't have to be. It's not just for simple reactions, right? It can be for these more complicated reactions, but as long as we know there's an addition reaction, pi bond is breaking somewhere, right? So, and again, let's have our generic triple bond. Right? I think I drew these too short, but, and you see here 2 of everything, but they're pretty much the same reactions, right? Ooh, this one. That one kind of got messed up. Sorry. CH3. And again, this is like the exact same as the one for the alkenes, right? So whatever here, right? Or they could have formed over here, but we formed it over here because why? It's a more substituted, right? And then this one just makes a bunch of halogens everywhere. There's like four, right? And then now this is where it kind of gets different. We make carbonyls, right? And now same thing with the alkenes. These prefer either anti, well not so much anti, but Markovnikov, things like that. So this one follows the Markovnikov. This one doesn't really matter because either way there's halogens everywhere. This one follows the Markovnikov, and again Markovnikov's rule, Mark's rule. Um, add to most substituted, right? So these halogens get added to the most substituted carbon. These doesn't really matter because either way you're adding halogens everywhere. This one is on the most substituted. This one is on the least substituted. So this one's anti mark. So that's pretty much the important things about that. Again, this is important, right? Na. So mark, anti-mark. Same thing as alkenes, BH3, boronation is anti-mark. So it's always going to be anti-mark. So, not too crazy, pretty repetitive, and you'll hear this a lot from your professors. They get repetitive, and OChem 2 is going to get repetitive as well. So, but that's good for you guys, right? Less things to study. If you that's why if you get one good concept, down, you're pretty much set. So hopefully that's what you guys are getting out of these. You know, it's well, at some point you'll have to memorize them, first, but then hopefully you guys catch on to these little things and start connecting and start kind of like making your life easier for you, right? You guys don't want to rememorize every single thing, right? Especially since the final's coming up, um, and you definitely don't want to memorize for every single one of your class, right? So, addition, reactions. Let's do some examples. So, find the products. Two HBr, EH3, and I feel like these are the same kind of things we kind of use as examples, but okay. And like I said, they get repetitive, but might as well do some practice out of it. So pause the video, take a second or a minute, and come back with your answers. So for this one, you guys should have done something like this, right? And again, they added over here because this is the most substituted carbon, right? Most substituted carbon. Mark. And this one, you guys should have gone 1, 2, 3, 4, 1, 2, 3, 4. This, right? So again, to the most substituted mark, BH3. And this one, you guys should have gone either or, right? Or, so you guys should have gotten two products for that, because either this side or this side, because it doesn't really matter, but, this is going to be anti-mark, anti-mark. So, nothing too crazy. Um, Again, pretty simple, pretty repetitive. Um, but hopefully, as you get through this, the best thing that you're doing right now is like fast forwarding, like I don't need this, I don't need this, I don't need this, because that means you got it right. And honestly, it doesn't get harder than this, right? So that's good. So let's go on. And this last part is probably going to be the most complicated type thing. So we have miscellaneous reactions. So for this first part, it's not really a reaction, it's more of a concept for acidity. So acidity is higher in sp, so meaning triple bonds, then double bonds, then single bonds, right? Because of that polarity, like I said in the, earlier, right? That polarity is making it more acidic, making it more a stronger bond, things like that. So that's what you look out for, especially on hydrogens. And acidity is the loss of hydrogens, right? Or willingness to lose a hydrogen. So, so um, sp triple bonds are gonna have really strong bonding to hydrogens, right? So it's just a stronger bond. It's not gonna want to lose it, so it's gonna be more acidic. So that's kind of the concept for that one. And now we go to, and I think you'll see this. Yeah, you'll see this again in OChem too. Um, Pretty late actually. Now that I think about it, I think it's pretty late. But you know, it's gonna be this concept is constitutional isomers, and you'll see why. They're constitutional isomers, the tautomerization, catalyzed by acid or base, right? So by either or, and this is kind of what they look like, right? So this is our enol, and this is our keto, and it prefers the keto because it's stronger bond, stronger double bond, right? So that's why it prefers keto, and you will see kind of later like why they do that. And pretty much these go back and forth, and think of it as resonance actually. Um, so this double bond just let me change the color. It basically just jumps over like this. So if you have an enol, it can turn to keto real quick, right? So don't forget about that. That's probably the biggest thing. What trips people up because they stop at enol without going to keto, and you got to make sure that you go all the way to keto, right? So go for keto, and think of it as the most stable, and obviously it is because it's a stronger bond, right? So yeah. So now let's go to what's the last one. This one's a big one. Bringing back our acetylide ions. So reaction with acetylide. Oh, hold on, sorry. Missed reactions, and this time it's with acetylide ions. So there's multiple ones, reaction, multiple reactions for these. So the general reaction is gonna be with this. And I'll set it like this. RC. So, right, our ethanol or acetylene, right, plus a base goes to RCC minus plus E plus, right? So that's, I'll stop there and let me give you where everything goes. So this takes that, um, this goes to that, things like that, and we end up with this. And now you have this, right? Now you see here that we have a nucleophile and electrophile. So E means electrophile, by the way. So now, obviously, nucleophiles and electrophiles are going to be attracted to each other, and we end up with, and I'm just going to do it in white. We end up with this. Basically, it's just an addition, right? Like that. So this is what we end up with, right? Now, we, this is the important part. This is our ion. This is, let me circle it. Hopefully this isn't getting confusing. So this is our acetylide ion, and this is the one we're interested in. Acetylide ion is the one we want. So basically, acetylide ions just attach to electrophiles, right? Attach to anything really, because this is a strong nucleophile. Strong nucleophile. And we know what strong nucleophiles do. They substitute out, right? So now let's do, you can do it with many scenarios. You can do it with many scenarios. This one is a generic scenario, but we can have something like this happen. Um, plus Rx, right? Or we can have plus um, R, and I did this as, it can either be secondary or tertiary. So secondary, tertiary, X. This R group can be secondary, tertiary, or we can have an epoxide, right? And these will lead into, this will become, this will undergo SN2, this will undergo E2, and this will undergo another SN2. So we end up with something like this. And because it's SN2, it's opposite, right? It's opposite, it's backside attack. Boom, right? And now this, you can have something like this, R, 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 right? From all those secondary, tertiary. So depending on which, plus C, right? And then this one, you just open it. And while you're opening it, since it's the backside, you make a new bond because again, you're adding this acetylide ion, right? So you just end up with this OH. It opens, right? And this is the new bond. New bond, right? So those are the scenarios. Again, don't forget about the SN2, right? SN2. So this R group will be different plane than this R group. This E2 just eliminating, right? So basically this R group joins whatever this R group is, right? And then we end up with just ethylene over here. So, you know, we talked about that. And then this one attacks like that, right? So actually, let me draw like that. Um, and same thing over here, right? So let's do some practice, and you can kind of see this in action, kind of. Hopefully, you guys follow that. But yeah, let's see. Let's see if you get it. So miscellaneous reactions. Okay. So first things first. Again, let's do. Let's label most least acidic hydrogen, right? So this hydrogen, this hydrogen, or these hydrogens, and actually, and then let's do this one. The tautomers, tautomer of this. Okay, so take a second, take a minute, pause the video, and show me what you guys got for your answers. Okay, so first one, the most acidic. You guys should have gotten this one right. Most and the least, right? Because this is just sp3, this is sp, and this is sp2, obviously, right? So not too crazy, but that's kind of what you have to look for with the acidity. That's what you kind of expect, right? Okay, what about the tautomer? We know the tautomer is ketone enol, right? So you guys should have gotten something like this, and it's a bit backwards, but oh, so there. And you guys should have gotten something like this, OH plus, right? So either or, because these two here are obviously what? The enol, right? This is the enol, and this is the ketone. And you can even do vice versa. What's the tautomer of these enols, right? Then you choose this one. So either or, nothing too crazy. Ketone enol again is just think of it as resonance, but with alcohols and carbonyls, right? So this could have gone over here or over here, right? So things like that. But we know we want ketos the best. Keto is always going to be the major product, right? So nothing too crazy. And yeah, there you go. That's kind of how you see it. So let's do more questions. I have a couple more here. Reaction. So this one, and this is going to be super easy now that you guys kind of saw the last question. Which represents keto enol pair? So this one and this one, or this one and this one. And then let's do find the products over these for here. Find the product. So first let's do hopefully this, yeah, let's just do all. Okay. H3CH2I, and then, okay, I think it'll fit. Okay, C, C, H. Okay, pause the video, give me your answers. Okay, so first one, this one's easy. You guys should have gotten this one, right? So again, I said it was kind of like resonance, right? It's not going to resonate all the way out here if it's the OH is right there, right? Um, this double bond could have gone either one of these places, right? But it's not going to go all the way out here, right? So that's not how resonance works. Um, so over here, that's where the double bond landed over there. So which ones are keto? Which ones are enol, right? Nothing too crazy. Okay, so this one, these two are kind of crazy. So for first, what's going on over here? What should be going through your head? Right, this is some type of what? Acetylide ion reaction, right? So acetylide ion. So where is the acetylide? Right. So this is our acetylide. So it's just an acetylide because it's not an ion yet. But if we take out the H here, right? There's an H over here. If we take that out, then it's going to be an acetylide ion. So you guys should have gotten something like this, right? So this is the original one. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, right? And let me color code it actually. So this is the reactant, right? And this part over here is this, right? So again, you just add them both together. So nothing too crazy. So let me change the color so it doesn't get all muddled up. Um, for this one, what again, same thing, right? But this time, this is already an acetylide ion, right? Or ion over here. And what do we say happens to the epoxides? It's an SN2. So which way is it going to attack? SN2 prefers primary, right? Primary over tertiary. So it's going to attack over here. And you guys should have gotten something like this. H, H, HO, and then a methyl group, CH3. And why? Because it attacks over here, and this opens up over there, making it the OH, right? So that's where this acetylide, and actually this is an ethylene ion, right? Attaches, and it's just these two, right? Is this, right? So super simple. You just attach it and go, attach it and go. Um, but again, don't forget that it's an SN2, right? If you were to attach it over here, it would have been wrong because this would have been, you know, a much different molecule because the triple bond would have been over here. So yeah, nothing too crazy. Again, this is our agenda. Outlines, hopefully we went over all those. Hopefully you guys learned something. Hopefully that helped, especially with the miscellaneous reactions. And I know acetylide ions get a little bit tricky, especially with the three different variations of it, things like that. Tautomerization is also a little bit funky. We're not used to that, but hopefully that helped out. So with that being said, this is your last, video for OChem 1. How do you guys feel? Hopefully, you know, everything's going well. Everything is going to go well, right? And yeah, thank you guys for watching these videos all these time. And hopefully I'll see you guys in OChem too. Okay, thank you guys. Bye.